right, let's wrap up this class with sort of summarize all of the different pieces that we've covered so far. So what have we learned? We've basically learned supervised learning techniques. And in particular, we focused on prediction. In the middle there, we had a little bit of a focus on confidence intervals, which is an inference problem, but most of the tools that we've learned in R are specific to prediction. And we've also, of course, learned and really hammered home the idea of the bias-variance trade-off. So these are kind of the big picture pieces that we've covered in this class. And so how do we ensure that we aren't overfitting when we're creating these prediction models, or that we're finding that sweet spot of the bias-variance trade-off? Well, we tune using an estimate of the test error, and we find a model that minimizes that. So when we're doing a regression problem, we often are minimizing the root mean squared error. When we're doing a classification problem, we're often trying to minimize the misclassification error. But in particular, we're minimizing the error using an estimate of the test error rather than the training error. So we're not using the same data we use to fit our model to then assess how well the model does. Because of course, if we did that, then we would just pick a very, very, very flexible model that essentially plays connect the dots between all of our training points. So how do we estimate test error? Well, there are three kind of ways that we talked about doing this. The first is just cross-validation. So the cross-validation error rate is an estimate of the test error. And so it is appropriate and just fine to just do cross-validation. You don't necessarily have to do that initial training testing split, because the cross-validation error that is given is an estimate for the test error. And we also talked about the validation set approach, where essentially you have one data set that you're training your model on, and then you have a separate data set that you use to test that model to see kind of how well it does. And then several times during the class, we've actually used a combination of both. And so at the beginning of an analysis, you've split your data into a training and test data sets, and then you've used cross-validation on the training data to be able to pick the right model, and then you've assessed how well that model did on your left-out testing data. And just to reiterate, that is, if you have the data, if you can afford to do that, if you have a large enough sample to split, that is a good way to do it. But often we don't have enough data to really do that initial split, which is okay. And in that case, it's totally appropriate to just do that first step, just estimate your model using cross-validation and pick your model using that cross-validation approach. And then you can report the test error from that cross-validation. And that's going to be an appropriate estimate of the test error. It might not be exactly the same as the estimate you get kind of locally when you do the split data set, but in the long run, if you were doing this many, many, many times, you'd expect those errors to basically converge and be similar. And so what types of models have we talked about? We've talked about two types of models, regression models and classification models. Where regression models cover models where you have a continuous outcome, and classification models cover the situation where you have categorical outcomes. And so under the regression setting, we've talked a lot about linear regression. And we've talked about ways to kind of improve on this, especially when you have a very large sample, or rather a very large number of predictors, and you need to be able to try to fit your model using those lots and lots of predictors. And so we've talked about ridge, lasso, and elastic net for sort of ways to penalize your regression such that it allows you to include a whole bunch of variables. And you can even have more variables than observations in the ridge or elastic net case. And with lasso, you can actually do variable selection because it's going to pull some of those variables to 0. And same with elastic net, since it uses kind of this hybrid between ridge and lasso. So some of those variables will get pulled to exactly 0 in that case too, which can be really helpful for variable selection. And then we talked about regression trees. So we talked about fitting decision trees in the regression setting. And finally, we finished with ensemble trees. And so we covered bag trees, random forest, and boosted trees. And so how do we actually do this? Well, using the tidy models package, basically we can fit all these different model specifications depending on which model we'd like to use. So for a linear regression, we would start with using the linear underscore reg function, and then we would set the engine to be LM. And so this is going to be a linear model or a linear regression model specification where the computational engine is LM. Or if we wanted to do ridge regression, we would edit this by updating the linear reg function with the penalty or the lambda value that we're interested in. And then we would set the mixture equal to 0 because that's going to be what we'll do ridge regression. And then we'll set the engine to glmnet instead of LM since that's the package that handles ridge, lasso, and elastic net. If we wanted to do lasso, we would still set the penalty the same as we would with ridge, but now instead of the mixture being 0, we're going to set the mixture to be 1, and this will allow for lasso to be performed. And we're using the same engine here, glmnet. And then with elastic net, it's the same as before, except now we're going to have a mixture that's between 0 and 1. So basically that falls somewhere between ridge and lasso. So elastic net is nice because it can basically leverage the nice parts of ridge, which are that you can have more predictors than you have observations, as well as the nice parts of lasso that some of those variables will be shrunk all the way to 0. Their coefficients will be shrunk to 0, which can be useful for variable selection. Okay, so then to do regression trees in R, instead of using that linear underscore reg function at the top, we're going to use decision underscore tree because this is going to be a decision tree. And we set the mode equal to regression to make sure that R knows that we are interested in fitting a regression tree instead of a classification tree. And when we learned about this, we learned that there were several different engines that you could set, but the one that we worked with was the R-part engine here for just your basic decision trees. And then moving into ensemble methods, if we're interested in bagging, the function that we use is actually the rand underscore forest because bagging is essentially, well, random forest is really a special case of bagging. I mean, you could think of it, I guess, either way. But random forest is a special case of bagging where or maybe bagging is a special case of random forest where the number of variables that's tried is equal to the total number of variables in your data set. And so here, I've set this random forest. My mode is equal to regression. mtry, I put 10 here because the data set that I'm working with has 10 predictor variables. But if you want to do bagging, you'd want to set that to be whatever number of variables that you have in your data set. And then you can set, obviously there are other parameters that we can set here as well, but this is the most basic form of bagging. And then we'll set our engine to ranger. If we're doing random forest, you can use the default, which is just going to which is going to estimate the number that it will try based on the defaults of this package. Or you could set that mtry to be something other than, essentially it's going to be something less than the total number of variables in the data set. We'll still want to make sure we set the mode equals regression because we want R to know that we're interested in fitting a regression tree, or a number of regression trees, in this case an ensemble of regression trees using the random forest method, as opposed to fitting an ensemble of classification trees. And then we still have the engine as ranger here. And then for boosting in R, we can use the boost underscore tree function. Again, we want to make sure we set our mode equal to regression. And for that, we used the xgboost package to be able to do boosting. So then we talked about classification, and the most basic way to fit a classification model was logistic regression. Very often, logistic regression actually performs very well. And it turns out for logistic regression, you can also use ridge, lasso, and elastic net. We didn't actually, we learned logistic before we learned ridge, lasso, and elastic net, so we didn't have this incorporated in that lab. But it turns out that you can use those same methods with a logistic regression model as well. And then you also can fit classification trees as well as ensemble trees for classification problems. And so recall in R, using the tidy models package, we can use the logistic underscore reg function to specify that we'd like to fit a logistic regression. And for the most basic logistic regression, we're going to set the engine to be GLM. And to do ridge with logistic regression, it's going to be very similar to the linear regression setting, except now instead of linear underscore reg, we have logistic underscore reg here at the beginning. And so we set the model type is logistic reg. We set the penalty, so the lambda value. And for ridge, the mixture is going to be 0. And then we still set the engine to be GLM net. And for lasso, it's going to be so similar. We still are using the logistic reg function. The penalty is 10, but now the mixture is going to be 1. And then finally for elastic net, it's going to be somewhere in between. So rather than setting the mixture to 0 or 1, it would be somewhere in between. And of course, we know if we were doing this in practice, we probably would be tuning some of these parameters using that tune function and cross-validation to be able to pick the appropriate penalty or the appropriate mixture. And for bagging, it's going to look just like what we saw for the regression problem, except now the mode is going to be classification. And same with random forest, and same with boosting. So there you have it. That's sort of a recap of what we've done so far in class. What I want you to do today is we're going to be working on a lab where you have you've been given a large data set and essentially an open-ended prompt that we're trying to predict. In this case, this is a data set of information about how people interact on Reddit. And so each line is an observation of somebody interacting on Reddit. Each column is a different kind of mode that they're interacting. And the thing that we're interested in predicting is whether or not they're an introvert or an extrovert. And so one of the columns in your data frame is their Myers-Briggs outcome. So it's going to be the first letter will be E if they're an extrovert or I if they're an introvert. For example, it might be ENFP. That's my Myers-Briggs. I don't know how much we trust Myers-Briggs, but that is my personal Myers-Briggs. And so if I were in this data set, my outcome would be ENFP. And what I want you to do is first create a new variable from that is going to classify whether or not someone was identified as having an E for their for the first letter of this outcome, or an I, indicating that they're an introvert for the first letter. And then I want you to use some combination of the predictors that are included in this data set to be able to predict whether or not the person is an introvert or an extrovert using this data. And so you're going to have to spend some time kind of getting to know this data set. I also want you to spend some time trying different models. You should try multiple different models here. You should try at least 3 different models. There should be tuning involved. You should make sure that you're accounting for the bias variance trade-off when you're trying to assess which model to pick. And then I want you to come up with a final model that you determine, and I want you to come up with final predictions and show kind of how well you can do in the total data set. So after you've picked the final model, I want you to refit it on the whole data set and then get a classification error rate on that. And I want you to explain along the way. I want you to basically explain all of the different methods that you chose, why you chose them. I want you to explain why you ended up with the final method you ended up with. I want you to interpret the final prediction model that you come out with. And finally, I want you to tie in some of what we've been talking about the past couple days about communication. And so think about kind of how this could be communicated easily to a general audience. And also think about kind of what assumptions or judgments you made along the way about the data itself, about what variables to include, and things like that. And make sure that you explicitly state those.